Hi everyone, I'm Hongkai, and today I'm going to talk about the probabilistic method and give you an introduction. And there are several sections in this lecture. And the first one will be we're talking about the lower bound to the Ramsey numbers. The probabilistic method is an important technique in combinatorics. In typical application, we wish to prove that a certain object or choice exists. And we'll introduce some randomness and show that the random construction works with positive probability. Yeah, and first we're going to talk about the Ramsey numbers. And what is a Ramsey number? From the definition, you can see that it is the smallest number smallest number n suggesting every red blue edge coloring of Kn, which Kn here means the n vertices complete graphs. There exists a red K sub K or blue K sub L. It's very clear. And what does the Ramsey theorem says about the Ramsey number? It says that for every K and L, which are all integers, positive integers, the Ramsey numbers of K and L are all exist, which means they're finite. Yeah. And I'll give out two proofs, which is the first one is Erdős original proof, and the second one we'll use another method, which is called the alternation method or the deletion method. And first, we're going to talk about the Erdős original proof about the lower bounds. The hypothesis says that if n choose k times 2 to the power of 1 minus k choose 2 is less than 1, then the Ramsey number of kk is greater than n. In other words, there exists a red-blue coloring of Kn with no red-blue coloring of Kn with no monochromatic K sub K. Here, monochromatic means a graph has the with all the vertices with the same color. And in proof, we're going to apply the union bound for events events E1 to E sub n m. The union bound says that the probability of all of them happening together will less or equal to the sum of each of the probability of each one happens, which is like this. This is called the union bound, and we usually think of each EI as bad event that we are trying to avoid. Okay, let's start the proof. First, we'll color edges of the biggest complete graph Kn with a blue independently and uniformly at random. This is what we're going to do in future a lot. Independently and uniformly at random. Then for each fixed subset, let's say S, which has K, which the S has K vertices. Of course, S is the subset of the set of vertices. And we'll let A sub S denote the event that S induces a monochromatic K sub K, a monochromatic complete graph of K vertices. And it's clearly that the probability of each such event happens is 2 to the power of 1 minus K choose 2, why is this number? Since there are two kinds of situations, which either blue or red, so there are two cases in the numerator, and for the denominator, well, how many cases are there in total? You can see that for each vertices, there are two possibilities, red and blue, either red and blue. And how many vertices are there? How many edges are there? There are k vertices, and it's a complete graph. So for each pair of vertices, there is an edge. So the total number of edges are k choose 2, and which give out this number. Then we can use the union bound. The probability of there exists a monochromatic k sub k is the probability of all the a sub s happens, which s ranges from all the all the subset of 1 to n with size k. This is the set of 1, 2 to n. And this probability, we apply the union bound. This is less than or equal to all the s with size k. Each of the probability of a sub s happens, and you can see that how many this kind of subset s are there. There are n choose k subset, and times the probability we deduced above. K choose 2. This is less to equals than 1, given here which given by the hypothesis. Therefore, we can conclude that with positive probability, no event a sub s occurs, which is exactly what we want, and it completes the proof. And remarks that we can also optimize n as a function of k. And in this step, we're going to you can try to do yourself. We'll use the Stirling's formula, and we'll get a quantitative bound, which is the Ramsey number of kk is greater than 1 over e squared of 2 times little o1 times k times 2 to the power of half of k. And then we're going to talk about another method, which is called the alternation method. And what is an alternation method? Instead of taking a random coloring and analyzing it, we first randomly color it, and then we fix some undesirable features. This is called alternation method. So you can see that after randomly coloring it, we delete something. So it's also called the deletion method. And the theorem says that for any k and n, you can see the hypothesis is much simple. There's no quantitative hypothesis there, and Ramsey number of kk is greater than n minus k n choose k times 2 to the power of 1 minus k choose 2. And for the proof, we're going to first following what I said before. First, we do some construction. We'll construct an edge coloring of a clique in 2 steps. The first step will be just what we did at the very beginning, randomly color each edge of the complete graph of k n vertices with red or blue. Of course, this step is done independently and uniformly at random. And the second step will be we delete exactly one vertex from every monochromatic k sub k, complete graph of k vertices. And what we got after this construction, this progress will give a two-colored, two-edge colored, since in graph coloring there is also a vertex coloring. Edge color click with no monochromatic k sub k. Since you can see in the second step, we destroyed all monochromatic clicks. And now let's analyze how many vertices are there in the end. And we will let x be the number of monochromatic k sub k's in the first step. And since we can see that the probability of each k being monochromatic this probability is 2 to the power of 1 minus k choose 2, which is also by this reason. You see that by linearity of expectation, the expectation of x is n choose k times this probability. Since you're totally vertices, and each kk is a subgraph of the complete graph of vertices. And in the second step, we delete at most the size of x number of vertices. Since you can see that we delete one vertex from each click, thus finally we have size greater or equal to n minus the size of x, which the expectation of it is n minus n choose k times 2 to the power of 1 minus k choose 2. Then we can conclude that with positive probability, the remaining graph has n minus n choose k times 2 to the power of 1 minus k choose 2 vertices. And you also no monochromatic kk construction. Yeah, and this completes the proof. And also, as the first method did and last, we can also optimize the choice of n in the theorem, and we'll obtain a quantitative amount, which is saying that the Ramsey number of k and k is greater or equal to 1 over e and little o 1 times k times 2 to the power of half k, which improves this one with a constant factor of square root of 2. Okay, then for the second part, we're going to talk about the Lovat's local lemma. And why we're going to talk about this one. Often we wish to avoid a set of, we call it bad events, E1 to En, like what we said above. And here are two extremes. The first extreme is from the union bound. If the sum of the probability of each event happens is less than 1, then the union bound tells us that we can avoid all bad events. And the second one is about independence. If all the bad events are independent, then the probability of none of them occurs will be the product of each of them not occurs, which is positive. What if? Then we have this question. What if there is some intermediate situation where the union bound is not good enough and the bad events are not independent, but there are only few dependencies? And then the Lovat's local lemma provides us a solution when each event is only independent with all but a small number of other events. So you can imagine. In my mind, I have the dependencies of each event are like this is the big three is the bad events, and it only depends on few of others. And here's one version of the Lovat's local lemma. Actually, in later we're going to talk. We'll have a whole chapter talking about the Lovat's local lemma. And here's a version of the Lovat's local lemma. And we're going to prove it later, so we're not going to prove it here. There are n random variables x1 to xn, and b1 and bm is in the sequence of 1 to n. And for each I, we let e sub I be the events that depends only on the variables indexed by bi, which you can see ei is allowed to depend only on this event. And we suppose for every little I in 1 to m, bi has non-empty intersections with at most the other bj's. And this is the hypothesis we have. The probability of each ei happens is less or equal than 1 over d and d plus 1 times e. Then we can conclude that with positive probability, none of the events ei occurs. Here, and using the Lovat's local lemma, we'll give one more improvement to the Ramsey number lower bound, which says that if k choose 2 times n choose k minus 2 plus 1 times 2 to the power of 1 minus k choose 2 is less than 1 over e, then the lower bound can be improved to n. Okay, let's prove it. And the first step we'll just get along with what we did before. We color the edges of k sub k with either red or blue, so uniformly and independently at random. And then we can see that for each k vertex subset, let's say S, and we'll let E sub S be the event that S induces a monochromatic k sub k. So the probability of this event happens is 2 to the power of 1 minus k choose 2. It's the third time we're doing this. And in the setup of the local lemma, we have only one independent random variable corresponding to each edge. we have one independent random variable corresponding to each edge. Each event E sub s depends only on the random variables and corresponding to the edges in S. On the variables corresponding to the edges in S. And then we can do some analysis. We can see that if there are two sets S and S prime, and they are both K vertex subset, and then do cliques share an edge if and only if the intersection of S and S prime is greater or equal to 2, since if they share an edge, then they must share at least 2 vertices. So for each kind of S, there at most K choose 2 times N choose K minus 2 choices. Choices of K vertex set S prime satisfying this inequality. So the lemma applies, provided that 2 to the power of 1 minus K choose 2 is less than 1 over E times 1 over K choose 2 times N choose K minus 2 plus 1. And in this case, we can conclude that with positive probability, none of the events E sub S occur. Which means an edge coloring with no monochromatic K sub K. And as we've done before, we can also get a lower bound by optimizing N. And for this one, we'll get Ramsey number is bounded by square root of 2 over E times O1 times K times 2 to the power of half K. Once again, it improves the previous bound by by a constant factor of root 2. And actually, this one is the best non-lower bound to RKK today, excitingly. And for the next section, we're going to talk about the set systems. And in extreme set theory, we often wish to understand the maximum size of a set system with some given property. And what is a set system? We say that a set system, let's say F, curly F, is a collection of subset of the set of 1 to n. That is, each element of the set system is a subset of this one. And we'll see some classic result from extremal set theory. It shows the clever probabilistic proof. And first one, we're going to talk about the Spencer's theorem. And we say that a set family F is an anti-chain if no elements of this F is a subset of another element of F. So it's anti-chain. I.e. the elements of this set family are pairwise incomparable by containment. And then naturally a question arises, what is the maximum number of sets in an anti-chain of subset of 1 to n? You can see that for the set F equals to all the subset of 1 to n of size k has size n choose k, and this is an anti-chain. And the size n choose k is maximized when k is taking floor, either upper floor or lower floor of heaven. And what does the Spencer's theorem tell us about? It says that if F is an anti-chain of subset of 1 to n, then the size of F will be less than or equal to n choose taking lower floor of n over 2. And in fact, we're not going to show Spencer's theorem. We're going to show a even stronger result. Which is the LYM theorem. Yeah, actually, the Spencer theorem tells us that actually this example is the best we can do now. And the stronger result, LYM inequality, says that if F is an anti-chain of subset of 1 to n, then the sum of all the subset of F and n choose the size of A, taking the 1 over it is less than or equal to 1. Then we're going to prove it. Yeah, actually this one, how we get the Spencer's theorem, and it follows since n choose size of A is less than or equal to n choose taking floor of half of n for all A. And it follows that 1 is greater or equal to this number in the hypothesis. Then this is greater or equal to size of F times n choose taking the lower floor of half n. Then it gives the Spencer theorem. Okay, wait, there's no space here. So we're going to prove the Spencer's theorem, or the LYM inequality. First we let sigma 1 to sigma n be a permutation of 1 to n. And this is also chosen uniformly at random. And we consider the chain. What is the chain? The first element is empty set, and the second one is the set of sigma 1, and second one is the third one contains sigma 1 and sigma 2, and the third one is also similar with it, sigma 1, sigma 2, sigma 3, and later until finally we have sigma 1 to sigma n. And we can see that for each A in the subset of 1 to n, we can let E sub A be the event that A appears in the both chain. Then we can see that each E sub A occurs if and only if all the elements of A appears first in the permutation sigma and followed by all the elements of 1 to n delete A. And since you can see from the chain, each chain n is the set of sigma 1 to sigma n minus 1. And we can see that the number of such permutation is the size of A taking factorial times n to the such size of A, also factorial. And hence we have that the probability of each A happens is the total number of permutation is n factorial, and we have this size of A factorial n minus size of A factorial, and you can see that from some algebra you can see this one equals to the number of n choose size of A taking power of -1. And since F is an anti-chain, if there are two sets in F being distinct, then the event of A and B appears in the both chain, which is EA and EB, cannot both open. It says that A and B cannot both occurs in the anti-chain, in the chain here. So the set of all E sub A, so that A is in the anti-chain, is a set of disjoint events, and thus their probabilities sum to at most 1, which gives the desired result. And then the second one, we're going to talk about the Probabilistic two-family theorems. And what does the theorem tell us? It says that there are A1 to AM, totally M, such R element sets, and B1 to BM are all S element sets. And each AI and BI are distinct for I, and all of them with different index are not distinct. There are some non-empty intersection. Then we can conclude that the size, the number of such B is less or equal to R plus 1 choose R, and R is the size of such A. And actually this bound is sharp. The equality can be held when AI ranges over all R element subset of 1 to R plus S, and the set BI is the complement of R1 to R and S. You can check it later by yourself, and we're going to go ahead. Let's give some application motivation for the Probabilistic two-family theorems in terms of transversals. And what is a transversal? given a set family F, we say that big T is a transversal for F if T intersect with S is non-empty for all other subset, which also says that T hits every element of this set family. And we'll let tau F, which is called the transversal number of F, being the size of the smallest transversal of F. And we say that F is tau critical if tau F prime is less than tau F whenever F prime is a proper subset of F. And here we have a question here. What is the maximum size of tau critical R uniform F with tau F equals to S plus 1? And we'll claim that this answer is R plus S, choose R. Indeed, we can let F equals to A1 to AM, and let BI and being an S element transversal of curly F to the AI for each I. And it satisfies our hypothesis introduced here. And then the condition is satisfied. Thus M is less than equal to R plus 1, choose R. And all. Also, we can see that conversely, if F is equal to all the subset of R plus S, 1 to R plus S with size R, this one is tau critical R uniform with tau F equals to S plus 1. And here is a more general statement on the Boloba's two-family theorem. We say that there are also A1 to AM and B1 to BM be finite sets, such as each of them with the same index are empty and non-empty. Intersection is non-empty with distinct index. And then the sum of the size of A1 and BI over the size of AI taking power of -1 is less than or equal to 1. And note that the Spencer's theorem and the LLM inequality are all special cases for this theorem, since if A1 to AM is an anti-chain, and we can set BI be the complement of AI for all I, and it will satisfy the hypothesis which gives the Spencer's theorem and LIM inequality. Okay. And the proof is actually a modification of the proof of the LIM inequality earlier. And when just consider a uniform random ordering of all elements that appears in the union of the sets, then we'll let EI be the event that all elements of AI appears before BI. then we can see that the probability of each such EI happens is the size of AI plus the size of BI choose the size of AI power of -1. And we'll know that each EIs are disjoint since EI and EJ both occurs, and what will happen? It would contradict the hypothesis for AI, BI, AJ, BJ. Thus, the sum of all the probability of EI happens is less than or equal to 1, which yield the claim inequality. There are also some beautiful linear algebraic proofs of the theorem and its extensions. And for the last thing in this section, we're going to talk about the Erdős-Corrado theorem on intersecting families. We say that a family F is intersecting if no two sets in this family are disjoint. Yeah. And here's an easy warm up. And what is the largest intersecting family of subsets of 1 to n? And one solution way is to include all sets that contain a fixed point as an element, and we can say the element 1 in this family will have size 2 to the power of n minus 1, and it's clearly intersecting. And then actually this is not, it's intersecting things, and each of them contains the element 1. And this is not the only example with size 2 to the power of n minus 1. You can try to think of other intersecting families with this size. And actually it turns out that we cannot do better than 2 to the power of n minus 1, since we can pair up each subset of one to n with its complement. And actually at most one of such a and complement, which is 1 to n taking out a, at most one of them can be in the intersecting family, so at most half of all such sets can be in one in the intersecting family. And the question becomes more interesting if we restrict to k uniform families. And the problem becomes, what is the largest intersecting family of k element subsets of n? And here's an example. F is all subsets containing the element 1, then F is intersecting. And the size of F is n minus 1, choose k minus 1. And then we give out the theorem, the Erdős-Corrado theorem. If k is greater or equal to than 2, then every intersecting family of k element subset of 1 to n has size of at most n minus 1, choose k minus 1. Which we can see that the example here are the best we can do here. And we should notice that the assumption n is greater than 2k is necessary, since if not in the case, then family of all k element subset of 1 to n is automatically intersecting by pigeonhole, saying that imagine there are n pigeonholes, and we put there n minus 1 pigeons, and if we're going to put the n plus 1 pigeons into the pigeonhole, then at least one of the pigeonhole has greater or equal than 2 pigeons. Okay, then we're going to and the proof here is a little bit complicated, and we're not going to show it. It is proved by considering a uniform random circular permutation of 1 to n, and we're going to bound the probability of the element, the event that each k element subset forms a so-called contiguous set on the circle. And yeah, it will involve more ideas which we are not going to show in the introductory section. Yeah, and then here comes the last section here. We're talking about the two colorable hypergraphs. And what is a hypergraph? We have graph introduced before. And what is hypergraph? And in graph, you can see that each edges contains 2 vertices, and for hypergraph, it can contain more than 2. And in this case, they are not called edges; they are called hyperedges. And a k-uniform hypergraph is a pair we denote by edge, which is hypergraph. And there are also 2 set of vertices and a set of edges. And V as a finite set, and E as a set of k elements, saying that each hyperedge contains exactly k vertices in it. Yeah, and you can see here, the size the set of edges are in the subset of the set of vertices choose k. And and we say that edges are colorable if vertices can be colored using k colors, so that no edge is monochromatic, which means that all the vertices in the edge are in the same color. Then this is monochromatic, and we'll let m to k denote the minimum number of. What is this type here? Number of edges in k uniform hypergraph that is not too colorable. It means that if we add 1 more edges, then it will still not be colorable. And there are some small values. Notice that in some literature, the 2 colorable are sometimes called the probability B. This is named after. This is not like type A and type B. It is named after, I think, someone named like Bernstein. Yeah, and here are some small values here. M2 is equal to 3. You can draw it here. Yeah, for 1k is equal to 2, then it is just a graph, and for 3 edges, it's not too colorable since it's very direct. And if m is 3, then if k is 3, then mk will be 7, and the example will be I can show it here. Yeah, you can check it by yourself through this graph. And M4 is 23. M4 and M4 is proved by exhaustive computer search in 2014. And each value of mk is unknown for k greater or equal than 5. However, we can get some asymptotic lower and upper bounds and by using the probability method. Yeah, and we have this first theorem. It's proved by Erdős. It says that mk is greater or equal to 2 to the power of k minus 1 for every k greater or equal than 2. In other words, every k uniform hypergraph with fewer than 2 to the power of k minus 1 edge is 2 colorable. And the proof is also very simple. We let there be m edges, where m here is is less than 2 to the power of k minus 1. And in a random 2 coloring, the probability that there is a monochromatic edge will be less than or equal to 2 to the power of minus k plus 1 times m less than 1. Yeah, and it gives us a proof. And remark that later we will prove a better lower bound mk greater asymptotically to 2 to the power of k times square root of k and times logarithm of k, which is the best up to date. Perhaps somewhat surprisingly, the state of the upper bound is also proved using probabilistic method by random construction. It also proved by Erdős in the same year. It says that an mk is less than or equal to k squared times 2 to the power of k up to linear. In other words, there exists a k uniform hypergraph with big O notation to k squared 2 to the power of k edges that is not too colorable. And yeah, maybe we can just state the proof here. I don't think it's very necessary, but yeah, let's do it. First, we let the size of V be n, and we write it in a way of k squared. Yeah, and this choice is motivated by displayed inequality below. And what is the display inequality? We'll show it later. We'll let H be the k uniform hypergraph obtained by choosing m edges let's say S1 to Sm independently and uniformly at random among this subset of vertices with size n. And given the coloring, and usually coloring is denoted by a function, and with let's say chi, it maps from the set of vertices to 1 and 2, since there are 2 vertices. If chi colors A vertices with 1 color and B vertices with the other color, then the probability that I write it here. The probability of edge Si is monochromatic under the color, actually this is a random edge under the random coloring. Okay, the probability is A choose K plus B choose K over N choose K. This is greater than equal than 2 times half of N choose K over N choose K. And we can expand it, and the numerator becomes 2 over 2 times over 2 minus 1 onto over 2 minus 1 plus 1. And we can delete, we can cancel the denominator of both the numerator and denominator here. And we got the denominator here will be n times n minus 1 onto n minus k plus 1. And greater than equal to 2 to the power, the numerator here is n over 2 minus k plus 1, and the denominator here is n minus k plus 1 to the power of k. Yeah, you can see it here. It's common usage in high school mathematics, I think. And this one equals to 2 to the power of minus k plus 1. Yeah, this step is deduced by scouting all the factors here. And 2 to the power of minus k plus 1 times 1 minus k minus 1 over n minus k plus 1 to the power of k. And this is 2 to the power of minus k plus 1. You can see that in the very beginning we set m equals to n squared, so it is 1 minus k plus 1, k minus 1 over k squared minus k plus 1 to the power of k, and greater than equal to a constant times 2 to the power of 2k for some constant c greater than 0. And since the edges are chosen independently at random, then for any coloring chi, the probability of chi is a proper coloring. Is less than equal to 1 minus this probability we got, constant times 2 to the power of minus k times power of m is less than equal to e to the power of negative c times 2 to the power of negative k times m. This step we use the inequality that 1 plus x is less than equal to e to the power of x for real x. And by union bound, we can see that the probability of the random hypergraph has a proper Q coloring is less than equal to the sum of it takes over all chi. The probability of each chi is a proper coloring. Less than equal to how many total chi's are there? There are 2 to the power of n. Since there are n vertices and each of them has two possibilities of color. And what we got here is e to the power of negative c times 2 to the power of negative k times m is less than 1 for some m equals to big O notation k squared 2 to the power of 2k to the power of k. And we can conclude that there exists a non-Q two colorable K uniform hypergraph with M edges, and it completes the proof. Yeah, and this is all for our first chapter here, and thanks for listening it. First, we let the size of V be n, and we write it in a way of k squared. Yeah, and this choice is motivated by displayed inequality below. And what is the display inequality? We'll show it later. We'll let H be the K uniform hypergraph obtained by choosing M edges let's say S1 to SM independently and uniformly at random among this subset of vertices with size n. And given the coloring, and usually coloring is denoted by a function, and let's say chi, it maps from the set of vertices to 1 and 2, since there are two vertices. If chi colors A vertices with one color and B vertices with the other color, then the probability that I write it here. The probability of edge Si is monochromatic under the color. Actually, this is a random edge under the random coloring. Okay. The probability is A choose K plus B choose K over N choose K. This is greater than equal than 2 times half of N choose K over N choose K. And we can expand it, and the numerator becomes 2 over 2 times over 2 minus 1 onto over 2 minus 1 plus 1. And we can cancel the denominator of both the numerator and denominator here. And we got the denominator here will be n times n minus 1 onto n minus k plus 1. And greater than equal to 2 to the power, the numerator here is n over 2 minus k plus 1, and denominator here is n minus k plus 1 to the power of k. Yeah, you can see it here. It's common used in high school mathematics, I think. And this one equals to 2 to the power of minus k plus 1. This step is deduced by scouting all the factors here. And 2 to the power of minus k plus 1 times 1 minus k minus 1 over n minus k plus 1 to the power of k. And this is 2 to the power of minus k plus 1. You can see that in the very beginning we set m equals to n squared, so it is 1 minus k plus 1, k minus 1 over k squared minus k plus 1 to the power of k, and greater than or equal to a constant times 2 to the power of 2k for some constant c greater than 0. And since the edges are chosen independently at random, then for any coloring chi, the probability of chi is a proper coloring. Is less than or equal to 1 minus this probability we got, constant times 2 to the power of minus k times power of m is less than or equal to e to the power of negative c times 2 to the power of negative k times m. This step we use the inequality that 1 plus x is less than or equal to e to the power of x for real x. And by union bound, we can see that the probability of the random hypergraph has a proper two coloring is less than or equal to the sum of it takes over all chi. The probability of each chi is a proper coloring. Less than or equal to how many total chi's are there? There are 2 to the power of n. Since there are n vertices and each of them has two possibilities of color. And what we got here is e to the power of negative c times 2 to the power of negative k times m is less than 1 for some m equals to big O notation k squared to the power of 2k to the power of k. And we can conclude that there exists a non-two colorable k uniform hypergraph with m edges, and it completes the proof. Yeah, and this is all for our first chapter here, and thanks for listening it.